somebody's saying something.
Hello, everyone. Welcome to our latest installment of AEC Tech Webinars. I'm Lissa Jersenko, Executive Assistant and Membership Coordinator for the Council. Our session today in the series is Alloy Flow Stress and the Tooling System, presented by Paul Robbins and Ken Chien of Castool Tooling Systems. All computer audio and telephone lines are muted, so if you have a question during the webinar, select Q&A from your toolbar and type your question in the dialog box. Our presenters will be able, hopefully at the end of the presentation, to address your questions, but if we run out of time, we'll see that those questions get answered. You can email me, Paul, or Ken directly if you have questions after the webinar. Just a little bit about our presenters. Paul Robbins is the son of a leading Toronto die maker. He received his postgraduate degree from the Schulich School of Business. He's worked in the light metal extrusion industry for more than 25 years and holds more than 20 international patents. As general manager of Castool, Paul has played an important role in some of the most influential development work in our industry. Today, Castool Tooling Systems hosts complete tooling systems for extruding light metal. Paul is well known for the articles that he's authored and for the many technical papers he's presented over the years. The most well-known phrase he is known for is temperature, temperature, temperature. From his article Super Extruders, which was published in 1997 in Light Metal Age. He's a committed advocate of the view that extrusion is a holistic process, and therefore components of the production systems should never be considered in isolation, but always in an interconnected part of the whole system. His website blogs continue to portray his views and visions of this ever-developing industry. His colleague Ken Chien is product director in Castool Tooling Systems, and prior to joining Castool, Ken spent 8 years doing research at the University of Toronto. He comes from a material science and metallurgical background about steel and aluminum, and Ken has been working on optimizing the aluminum extrusion tooling. He also has a dual role as Asia sales manager and has been visiting customers worldwide to gain a broader and deeper understanding of products and their performance. The unique dual role enables Ken to understand received feedback from customers directly and improve tooling. Both of these distinguished gentlemen have been important contributors to ET events and other AEC events as well, and published proceedings. And now it gives me great pleasure to turn the webinar over to Paul and Ken.
Good afternoon, and thank you very much. You'll see my picture on the left-hand side is a little bit different than it usually is because I was lucky enough to be hit by lightning last week. So as the monk in Thailand told me, 100% of the people in Thailand that get hit by lightning die. So I guess I'm a very lucky guy. And Ken?
Good afternoon, everyone. It's my pleasure to do the presentation of Paul Robbins today. Just like he said, he's a lucky guy, and I'm a lucky guy to do the presentation with him as well.
Okay, flow stress. Flow stress is a rather simple way at looking the force required to deform material, in which case we're looking at alloys of aluminum. Flow stress is controlled by the chemistry of the alloy, the temperature of the alloy, and there's not a linear relationship, it's an exponential relationship between temperature and flow stress. Also by the ram speed and the extrusion ratio.
So the factors that would affect the flow stress, if you look at different type of alloys, 6061 has higher flow stress compared to 6063, so it's harder to extrude. Also, the temperature affects its flow stress as well. At a higher temperature, the flow stress is lower, so it's easier to extrude through the die. And when you try to deform the material faster, which is increasing speed of ram speed, then you will also increase the flow stress, so make it harder to extrude. And obviously, when extrusion ratio is high, then it will be harder to extrude as well.
When we look at ram speed, what's interesting with 6063 alloy If we double the RAM speed, we only increase flow stress by 10%. So most people would believe or think that if you would double your RAM speed, that your flow stress would go up similar. But it's actually quite easy to go faster.
But then when we look at the temperature effect, it's exponential. So all alloys are temperature sensitive. You can see 7000 series alloy. Every time when you drop the temperature by 20 degrees Celsius, the flow stress increased by 20%. And 6063, 20 degrees Celsius by 10%. Compared to Paul just mentioned, RAM speed is relatively insensitive, and temperature is very, very sensitive to flow stress.
What happens with temperature is if you're only extruding 6063 alloy and comparatively simple shapes, and you have poor temperature control, you can probably survive. But as you start moving into 6061, 6082, and temperature has more effect on flow stress, when you have temperature instability or poor control, you have a hard time making profit. When we start looking at wall thickness, flow stress also gets involved. And I think this is something that a lot of people forget. If you're doing a sort of a standard window shape or something today, you may have minimum wall thicknesses down as low as 20 to 25 thou. And 6063 is an adequate alloy for doing this. If you want to do heat exchanger tubing or precision tubing, where your wall thicknesses can get down to 8 to 10 thou and are often less than 15 thou, the reality is the flow stress of 6063 alloy does not enable you to extrude that thin of a wall. Basically, the die would plug and nothing would come out the other end. So we go to alloys with lower flow stress that can also extrude thinner walls.
But if you go to the other extreme of the spectrum, you're looking for high-strength alloy, for example, 7000 series alloy. The minimum wall thickness is higher than 6000 and 3000, so that's why you have to use this profile, and then there's a minimum wall thickness you can only extrude through for the strength and the alloy that you want to get out of it.
What's interesting is the minimum aperture or wall thickness that you can extrude through the die is also very similar to the gap between the dummy block and the liner. So the aperture or gap between your dummy block and liner at temperature during operation is virtually identical to the die aperture.
So typically what people are trying to aim for when they try to look at their press limit diagram is, you can see at the bottom, you see it's a billet temperature. And people try to narrow the billet temperature so they can improve the extrusion speed. So they bump it from red to the green, so they increase their profits. However,
yeah, that's a little bit. When you take a look at the red line here, if you had control of your billet temperature of maybe plus or minus 20 degree F or maybe 30 degrees even, because you have instability in your billet temperature, it doesn't enable you to hit the maximum or the peak in this triangle. What you end up doing is having to reduce your RAM speed relative to your billet temperature. Every good extruder wants to control the billet temperature within, say, plus or minus 10 degrees or better, which enables them to operate as close to the peak in this area as possible. And again, our limitations here are flow stress on the left side, because in this area you don't have enough pressure on your press, and these are the actual alloy effects. As you get above these temperatures, you have tearing and other defects. When you look at any alloy, and 6063 is a good alloy to look at, the chemistry is actually quite broad. So if you go tensile strength against extrusion speed, and within this sort of matrix here, we have different mag silica recipes. And as we change the mag silica, we can actually change the flow stress of the alloy. The super extruder wants to operate as close to, depending on the tensile strength he wants, as far to the right as possible. By doing this, he's leaning out the alloy and reducing the flow stress.
So what's interesting is if you look at the press limit diagram for super extruders, they have a different set of diagrams. They are able to use, by using linear alloy with a high performance die, they are able to bump up the maximum speed to a newer and maximum speed. So if you look at this diagram, right now is steeper, so the peak is higher. They do have additional productivity gain out of it.
And again, this is all through temperature control. You know, the first, boy, this is a complicated one. Again, we had a rather wide triangle here, and that the average extruder is trying to get up to this point. And then we tape our super extruder, and we change all of the rules. And by that, we're seeing ram speeds about 40% faster than the average extruder. With die design, the die creates resistance to the extrusion process. And you know, maybe I can apologize a little bit. The rate that we have to go to get this into the 40 to 50 minutes time span is quite quick. So again, apologies. And if there's questions afterwards, you're welcome to pose them. The die creates resistance to the extrusion process. And this is to give us both mechanical and thermal properties. The die designer's objective is to reduce the pressure difference between the entry and the exit faces of the die. So basically, to make the die as easy to push as possible so that you can use the coldest billet possible to attain your exit speed and mechanical properties. This is a look now at what is a rather thick die with rather small ports. And typically these are used to compensate for poor billet and die temperature control. Very often, last week I was with 7 different extruders through Southeast Asia, and all the die correctors want thick dies with long bearings. And the reason they want thick dies with long bearings is because they do so much die correction because of temperature instability that they need something to work with. If they were given a thin die with open ports with short bearings, there wouldn't be enough material for them to control the die. The problem is a thick die with long bearings is a slow die. A slow die is a die that requires a hot billet temperature and is going to end up having a rather slow ram speed. The alternative is a high-performance die. They require temperature management of the billet, die, and the container. And very often the same people that are using these dies are using lean alloys. What they're achieving is ram speeds typically 40 to 50% faster than the average that we see in the marketplace. So, you know, a lot of extruders say, great, you know, I want one of those high-performance dies. But unless your billet temperature is plus or minus 10F, your die temperature is plus or minus 10F, your container is stable and plus or minus 10 degrees Fahrenheit, unfortunately, it won't work. Your die corrector will come back to you and say, look, we tried that die, we got lousy profiles out of it, give me a thick die with long bearing so I can fix your problem. When we look at the cost basis, the super extruders that are running with these fast ram speeds, their costs are significantly less than the standard extruder. And by significant, we're looking at 40% difference. So by running 40% faster ram speeds, they're reducing their cost, if you look at $1,000 per hour press cost, by about 40%, from 33 cents per pound to 20 cents per pound. Is it worth it? I don't know. That's up for you guys to tell us, I guess. But the return on investment from managing temperature of the billet, temperature of the container, temperature of your die, your exit temperature, your quench temperature, and your aging temperature seem to be pretty straightforward to me.
So what you wanted to do is, starting from the first billet, there's no delay in acceleration of the run speed. So what the temperature of the die coming out of the die oven has to be perfect, and also the billet temperature has to be perfect. Both of them has to be controlled in relative tight windows, temperature windows.
Last week, again, I did 7 presentations to 7 extruders. We had maybe 25 to 50 people on each presentation, and just about every extruder was using 2 to 4 billets to start every die. The only reason you use startup billets is because your dies are cold. And if you're using startup billets to heat your die, one, it's very expensive. Just think, you could be using those billets to, make saleable profiles instead of heating your die. And if we go back to a strong die, if you had a weak die, you would break the die. So the die designs that they're using to start the dies with, say, 2 to 4 billets are also strong, slow dies. By no means have they any chance whatsoever to be a super extruder, because their billets out of control, their dies are out of control, their billets are rich, which makes them strong with high flow stress. Their dies are too strong, which increases flow stress, which causes them to use hot billet temperatures, slow ram speeds to get their exit. I said it a number of times last week, and I guess a lot of people got upset with me, is chest ovens don't work. If the goal is to have a die that's plus or minus 10 degrees Fahrenheit uniformly from billet temperature, and you're heating dies with chest ovens, it's impossible to do that. Chest ovens produce cold dies, inconsistent dies, and typically dies are in them for too long and have oxidized bearings.
So you can see on the left-hand side, you can see the bearing is oxidized. And also on your right-hand side, looking at the profile, clearly you can see the die lines because of oxidized bearings. And there is no way that you were able to put nitrogen in the oven to get rid of oxidations, because you only need very minimal of oxygen to do the damage.
Well, unfortunately, the die bearing being an EDM surface attracts the oxides faster than any other item in the die oven. Another big problem, and just to touch base with it, the adhesive layer on the die bearing, if you have a lot of people put fans in their die ovens, and basically the fan's job is to pull the air of the factory and push it into the die oven to heat the dies quicker through convection. The worst thing you can possibly do is take the dirt from the factory and push it into your die oven, because it's going to end up in your die bearings. Single cell die ovens, basically heating one die at a time. I would say 100% of the super extruders in the world today heat one die in one oven. And it's the only way of having 100% control over your die temperature. And we hear all the excuses from all of the, I would say, poor to average extruders around the world in why it's impossible to heat dies one at a time. But the reality is it works. And I haven't pulled this picture up for years, but this picture is from 1986. And it's from an extruder that I have a great deal of respect from and probably taught me about die heating. Heating one die at a time works, and it's the only way to get 100% control over your die temperature and enable you to be very aggressive with die design so that you can reduce the pressure required, use a colder billet, and a faster RAM speed.
Even when you have a perfect die coming out of the die oven, and the die can cool down quickly in the air around 10 degrees Fahrenheit per minute, or 20 degrees Fahrenheit per minute in the die slide. So you're not really getting the temperature that you think you are getting when you leave the die in the air for too long, or if you leave the die in the die slide for too long. And then when you start to extrude, you will start to see the flow stress is going to get affected because of the die temperatures.
And you also want to be recording these times. So you want to record when the die goes into your die oven, when the die comes out of the die oven, and when the die is used. If you have a 3 to 5 minute delay because you have a butt stuck on your butt knocker, or you're cleaning aluminum from the liner seal face, in 3 minutes your die is going to lose 60 degrees. 5 minutes it's going to lose 100 degrees. As a rule of thumb for 6063 alloys, we say 10 degrees Fahrenheit relates to about 1% rate of flow. So for every 10 degrees colder your die is than billet temperature, it requires 1% more force, or the flow through the die is reduced by 1%. So if the die was 100 degrees colder than your billet 860, your die 760, it would take 10% more effort to extrude the die. We get into a lot of die correction as well, and we find that probably about 90% of all die correction is correcting the die for temperature, not because the die was made improperly. So even if we take the die perfectly from the die oven, we sit it in the die slide, and we leave it there for 3 to 5 minutes. The bottom of the die is going to lose more heat than the top of the die through conduction between the die and the die slide. So your nose piece, or if you're running a 2-hole, the top holes are going to go faster than the bottom holes. Say we left the die in for 5 minutes, and we reduce the temperature of the die in the bottom by 100 degrees. Back to my rule of thumb, we would expect about 10% more flow through the top of the die than the bottom of the die. The die corrector would choke the top bearings, and the next time the die goes to the press, if you left it in the die slide for 5 minutes again, it would be fine. But if you don't get the butt stuck on the butt knocker this time, and you actually extrude quickly, the back holes now will hold back, and the bottom holes will go through. And your die corrector will be chasing this. And again, temperature affects flow rates. Whether it's the container affecting the die slide affecting the die, even if you use chest ovens tend to heat the die from the bottom up. So when you bring a die out of the chest oven, typically the bottom of the die will be hotter than the top of the die. If you leave the die in the die slide for 5 minutes, the bottom of the die will be colder than the top of the die. We'll talk about the container effect next, but typically the top of the container is hotter than the bottom of the container, anywhere from 50 to 100 degrees. So after you extrude anywhere from 5 to 7 billets, the top of the die will become hotter than the bottom of the die, and again, the flow or your runouts through the top of the die will now be faster. It's very difficult to correct a die for temperature, if not impossible. The biggest problem with the container is that it's big. And containers are anywhere from 5 to, I think the biggest container we do is 37 tons. The die in comparison is hundreds of, I was going to say kilos, being a Canadian, but hundreds of pounds. There's a complete imbalance. And because the mass of the container is greater, the thermal mass is also greater, so the container controls the die.
And also, when people try to heat up the container, there are several options, and we see a lot of people, they still use external heaters. In order for the liner to be at extrusion temperature, that you need to have a high temperature from the shell or container shell, which can be around 700 degrees Celsius. And we know even for hard working tool steel, H13 would not be able to withstand that temperature for a long time, and you're going to anneal the container. When you anneal the container, the mechanical strength of the container or integrity of the container is gone. When you extrude, the liner is going to be bellied. And because of profile, it's hotter outside and colder inside, you're going to see temperature swing and temperature changes. And the liner can be too hot during extrusion as well.
This is a typical container that's being relined, and you can see where it's being bellied in the one part. And we'll talk about it a bit more in a couple of slides later, but the interface between your dummy block and the liner is very sensitive, and the gap between your dummy block and your liner is very similar to the aperture in the die. So if this gap is increased, you're going to have a minimum blow-by. The other problem is these areas of bellying tend to collect the oxides and inverse segregation in your billet. And as they're collected in these depressions, they can be released into your profile randomly.
So all we want, or what we are asking, the goal of container is thermal stability. That thermal stability can give you quality extrusions and high productivity, and also mechanical alignment, because when you expand the container, because due to its diameter, the alignment can be off, and we want to have a round cylindrical bore between the liner and the dummy block. So to rephrase again, thermal stability of the container is the key.
If we take a look back at our external heating, and actually we'll go with this one. A lot of extruders that I visited last week operate 6 days a week. On Sundays, basically, they set their liner at 800 and some odd degrees Fahrenheit, and the heating elements are running between 13 and 1400 degrees. So by Monday morning, the container housing is easily 800 degrees, if not 900 degrees. When the container housing is hot, it actually lifts the container and ruins the alignment between your container and your die and your container and stem. So it's not just about temperature. Temperature also affects mechanical alignment.
Also, the temperature of the liner would affect the billet skin flow. What you want is you want to have a consistent temperature differential between billet and your liner surface around 50 to 60 Fahrenheit. So you can hold back the surface defects and stay there as a skin, and you can use a cold cleanup block to clean after. If you don't know your temperature of the liner surface, you don't know if the skin defect is going to stay at the shell there or will go into your profile extrusions. So it could be just anything if you don't control the liner temperature, or if you don't have the thermal stability of your liner.
Again, the goal is to keep 100% of the inverse segregation and oxides in the butt. What we don't want to happen is any of that basically leaking into the profile. You know, we can help it by keeping the port openings away from the liner. We can help it by doing all sorts of good housekeeping things. But if your liner is unstable or approaching billet temperatures, the oxides that we want to hold back into the butt on the liner wall are going to be leaking into your profile. Last week, again, I was at 7 different extruders, and every one of them brought out lots of samples to show us of bad surface finish. And when surface finish is random, it's typically the fault of the container, not of your alloy and not of different things. Just about every extruder I visited had installed billet brushes. I wouldn't say, cleaner billets are great things, but these surface defects weren't being caused because people had dirty billets. They were being caused because they had hot liners, unstable liners, and bellied liners. It was a matter of inverse segregation and oxides being leaked into the profiles randomly.
So the trick is, how do you balance the heat in your container? Because container is a big chunk of mass and cylindrical, and there's no way to reach the hot deformation zones. But what we can do, we can do a simple, quick heat balance between extrusion profile and the billet coming in, and also the extrusion of heat of deformations. You can see on this on the top of the graph. So the only thing that we can control is component C, because component A is the billet comes in, and the D is the profile goes out, and also the extrusion curve for the component B. But component C is, how do you take away the temperature? But we can take away the temperature by manipulate these equations, which is pretty simple. There are three main parameters here. One will be the temperature gradient of the container. The second one would be the thermal conductivity of the material used. And also the last one is the surface area. So if you compare three different container designs, then you can place your heater in the different locations. Still, a lot of people use external heated elements. We see some people use center of mass heaters, and we think the proper one, or the best one, is if you put a heater close to the liner. You can see from this diagram clearly it depicts the temperature within the container. The first one on your left, you see the heater is on the outside, and the thermocouple is in the middle of the container. In the middle one, you see the container is red, it's hot. On the right side, you see the temperature close to the liner is the extrusion temperature, but in the outer shell, the container is colder. So what would that do to your temperature gradient, which is the first component we talk about? If you have an externally heated container, you see on the x-axis is the number of billets from 0 to 200 billets. You see you have a temperature swing from positive gradient to negative gradient. That means sometimes your container is actually providing more heat than you needed to your liner. So your liner temperature is not stable at all. It can be hotter than your liner, hotter than your billet, or colder than your billet at random.
And when it's hotter, you're going to get type A inflow. So typically, if you have external heaters and you operate 6 days a week, every Monday afternoon of every week, you're going to have bad surface finish until the outside of the mantle is actually cooled so that you have the proper gradient and you're able to dissipate heat. And even when you have center of the mass, unfortunately, we have instability. The liners tend to go from set point hotter. There's no way of actually getting the liner down and stable where we'd like it. One other benefit, if we go back a slide, is energy consumption. As you can see, by having a hot container and a hot container housing costs a lot of money. If you actually allow the container housing to be 200, 250 degrees Fahrenheit, and your container to have both a longitudinal and diametrical gradient, we can reduce energy costs anywhere from 50 to about 70%, which is considerable when you look after, day after day, month after month.
So that the second component we're talking about is the thermal conductivity of the container itself. What we think would be the proper material to use would be the 4340, because it has a high thermal conductivity compared to H13 and H11. Also, its toughness is also doubled compared to H13 and H11. And what's interesting, if you couple the thermal conductivity and temperature gradient together, you see when you put the heater close to the liner, you see the temperature gradient multiplied by the right material, 4340 material, compared to if you put the heater at the center of the mass and with the conventional H13 material, you see the heat dissipation rates are vastly different. So that's why you see a lot of containers, as they extrude, the temperature of the liner starts to creep up because the container doesn't have the ability to dissipate the heat. And obviously, the blue one is the worst one, which is external clamshell type. You have positive and then goes to negative. So you take away heat and you supply heat to your liner and to your billet as well.
So we talked quickly about sort of a diametrical gradient. Basically, by moving the heating elements close to the liner, we get a diametrical gradient. So if our billet was 860 degrees, we would like our liner to be maybe 800, 810. The outside of the container maybe to be 400, 450, and our container housing to be 250. That's our diametrical gradient. We also want to have a longitudinal gradient. There's no reason whatsoever to have the entrance of the container the same temperature as the exit. And if we provide a taper longitudinally, we allow more dissipation. So we can dissipate heat from the liner to the outside of the mantle or diametrically, and we can also dissipate it from the exit to the entrance.
And sometimes for some profile that requires very high productivity, there is too much heat to dissipate by the container itself. But we can put complementary cooling on the OD of the container.
Just one sec, Ken. The reason most people air cool the liner when they have heating elements in the center of the mass is that the combination of H11 or H13 or 2343 and 2344 and having the heaters in the center of the mass doesn't give enough heat dissipation and the liner gets too hot. So the reason people do air cooling between their mantle and the liner is to cool the liner down to reduce type A inflow. As you get involved with, say, microtubing and 1100 and 3000 series alloy with extremely thin wall thicknesses and extremely high extrusion rates, even a container done with 4340 with heating elements close to the liner may need assistance as far as dissipating heat. And I would say, except in these extreme circumstances, this type of container doesn't require air cooling. When it does, we put on the outside of the mantle basically heat sinks and run air through it to give us more. We have the same situation. There's a number of presses still in the United States that used to be 6-inch presses, and people have opened up the liners, are now running 7-inch. The container that was built for the 6-inch doesn't have the mass to be able to dissipate the heat at the rate that it needs to maintain a stable liner condition. So when we're dealing with rather small diameter containers or small mass with bigger billets, we'll still do the same thing. We'll actually put the heat sink on the outside of the mantle to enable us to dissipate more heat to get a stable liner. We also worry about the physical dimensions of the liner during extrusion. All of the people that make containers put a shrink fit between the liner and mantle to try to add strength. If a 3-piece container is definitely stronger than a 2-piece container. What's interesting, if we look at a standard sort of 40-inch container for an 8-inch billet, the amount of expansion on the bore of a 2-piece well-made container is about 35 thou. And when we look at the dummy block and the container, we work this into our calculations. So we may allow somewhere 20 to the 30 thou clearance at room temperature between the dummy block and the container. We may have about 30 to 35 thou expansion in the dummy block during operation. And we allow for about 35 thou deflection of the container board during extrusion and everything is fine. What happens if we suddenly go to a 60-inch container? The amount of expansion of the liner bore goes up by close to 50%. So the same container, same dimensions that was 40 inches long, will expand about 50 thou. And depending on the flow stress of the alloy that we're extruding, the aperture between your dummy block and your liner may be big enough to allow aluminum seepage between the two now. If we then make that 60-inch container three-piece with the proper shrink fit, we can decrease the expansion of the bore to 33 thou versus 50 thou. Basically bring it back into a stable condition where we're not going to be affected by aluminum blowfly in the liner. This seems to be something that a lot of people are, I don't know, not paying much attention to in the marketplace. And it's not the dummy block's fault. If you have a dummy block with a 60-inch container and your container is two pieces, you're going to have a problem. This is just a chart that Ken did up for me, and we looked at a 40, 50, 55, and 60-inch container. Two-piece, the 40-inch container will expand about 35 thou, three-piece 23 thou, and again, as dummy block and tooling system manufacturers, we don't worry about 35 thou expansion. We can work with that between the expansion of the dummy block and the flow stress of the alloy. As we get into 50 inches, we're probably still okay as long as it's not soft alloy with 45 thou expansion of the bore. As we get into containers that are 55, 60-inch long or longer, there's too much mechanical expansion in the bore to be able to put a dummy block in there and control the aluminum and aluminum flow-by. So in all cases, when we start getting above 50 inches, we recommend going to a three-piece container to be able to control the expansion. And again, if we're doing soft alloy, we would tend to, do it sooner with shorter containers. And again, this minimum gap for 3000 series alloys is about 15 thou. 6000 series alloys is about 25 thou, and for 7000 series is about 40 thou. So as we get involved with alloys with lower flow stresses, the gap or critical gap between the dummy block and container at operating parameters becomes smaller. Dummy block clearance is alloy dependent. Clearance becomes more critical with soft alloys than it is with hard alloys. Typical expansion on a dummy block is 25 to 35 thousandths on diameter. What we want to do is the dummy block to collapse back to as close to nominal as possible after the push. So when the dummy block comes back through the liner bore, we want it to go back to nominal size. We want the dummy block to yield as little as possible. All dummy blocks yield, so we're going to get somewhere 3 to 5 thou per on diameter yield of a dummy block just about immediately. What we would hope to do is to curtail or stop any further yielding as long as possible. Deformation is typically because of time and pressure, so we want to be able to cope and deal with pressure and time through design. Temperature affects clearance. If you put a cold dummy block in your press and you start extruding, you've increased the operating clearance substantially. You're probably going to get immediate blow-by. You also change the mechanical properties of the dummy block. A lot of presses have gone to longer billet these days. With longer billet, we've increased the amount of friction lost between the billet and the container. And typically about 30% of our total press pressure is lost to friction between the billet and the container. If we increase the billet length by 10 inches or 20 inches, we need more pressure to be able to break through the die. What would happen if we went from a 40 to a 60-inch billet and we had adequate pressure for a 40-inch billet at 50 or 60 inches, more of that pressure would go to friction and we wouldn't be able to break through the die. So we actually have to increase the tonnage capabilities of the press. Unfortunately, Ken's done a lot of work on this, and I'll like him to explain what happens.
So what happens is when you increase the pressure or specific pressure that dummy block sees.
May I just add one thing, is that the die doesn't see any more pressure.
Yeah.
It's just the dummy block.
It's just the dummy block, because the friction is taking care of the other side, now the die side. So the dummy block is already operating around its limit already. Now we increase the pressure, the specific pressure dummy block sees, and you can see on this study, the top one is around 100,000 psi. You start to see some red areas, which the block is starting to yield. When you increase by 20%, which with a longer billet, 120,000 psi, a lot of them became red. So red means the block is yielded, and so when you expand, the nominal diameter of the dummy block is going to be different, and it's going to be collapsed differently as well. So then we need to come up with a new dummy block that can withstand higher pressure. So we increase the column strength by 15%, rear column strength, and the pad area by 35% to withstand the higher pressure that we just mentioned. And this one, the quick study shows that on the top is the replaceable ring dummy block at 120,000 psi, and the bottom one is the new replaceable ring at 120,000 psi. The yielding on the block is minimized so that the block is able to function properly, open it properly, collapse properly, and with repeated cycles at 120,000 psi's. What we are trying to achieve is through high pressure dummy block and a stable container bore, we want to have an efficient interaction of a container, liner, and a dummy block. So when you start to push the skin or the clearance between the active clearance between liner bore and the dummy block is consistent, and when you retract, the dummy block is not yielding, the nominal stays the same, so you can retract and leave the skin not touching or dragging the aluminum skin out of the dummy block or out of a liner board as well. The graph just shows that we did a simulation study on 6063 alloy, and you can see from...
It's in a metric.
It's in a metric, so that's about 8 thou. That's about 8 thou for the aluminum skin. So you can see the aluminum skin is quite consistent from start of push, 10 seconds, to the end of the push, 45 seconds. So that's what we want, to have a consistent aluminum skin. And that tells you the bore is concentric, round, and straight. The liner is stable. There's no alignment problem or issue between container and dummy block as well.
So flow stress matters, and flow stress is an easy way for us to understand the interaction between the billet, the container, and the die. Alloy affects this as we get into softer alloys with lower flow stresses. The critical gap in the die, or the aperture, if you want to extrude extremely thin wall shapes, the critical gap between your dummy block and your container is the same as the die. So those people that are doing precision tubing, you want it pretty much be a 3-piece container because we want to decrease the deflection in the bore. we want to run with as minimum clearances as possible. So typically we run reduced expansion, reduced clearance, 3-piece containers, and because the alloy is very temperature sensitive as well, we want to control the liner bore typically plus or minus 5 degrees Fahrenheit for precision tubing. Extrusion ratio and profile wall thickness I just mentioned. Thermal management of the billet plus or minus 10 degrees. If it's precision tubing, plus or minus 5 degrees. The container plus or minus 10, precision tubing plus or minus 5, and the die the same. The container dummy block interaction is extremely important. If you're going to pay extra money for clean billet, you have to control the skin thickness, and you need to control how it is adhering to the liner. If your liner is unstable or bellied, you're going to have surface finish problems. You have no choice. Is that it? Yep. Thanks, Ken. Okay. We're open for questions.
We do have a couple of questions. The first one, Paul and Ken, is how did you calculate that a 60-inch container will double in expansion? The thermal expansion is based on the radius, so it shouldn't make a difference.
I can share with you, there's a simple equation that actually take into actual stress, because the longer the container, you have more friction loss due to more stress due to friction, and friction there, it's actually contributing to the expansion of the liner bore. That's how you calculate, even on the same specific pressure, the expansion of the bore is going to be different because of friction there. And it's because of longer container, you have a more friction in terms of percentage-wise.
And that's something that a lot of people seem to be missing now, is the longer containers have more deflection. And there's a number of people out there with billets 55 to 65 inches long, and it's been a nightmare.
Okay,
Yep.
The next question is how long should you let a dummy block heat up before using, or what temperature should the dummy block be before use?
The dummy block should be the same as your billet temperature. And basically, you're looking at about 1 hour per inch of cross-section. So if you have a 7-inch dummy block, you're looking at about 3 hours. If you have a 12-inch dummy block, you're looking at about 5 hours. That would be in, I'd say, a chest oven. If you were doing it in a single-cell die oven, it would be a bit quicker.
Okay, while we're waiting a couple of minutes to see if any more questions come in, first of all, I wanted to thank you, Paul and Ken. That was a terrific presentation. Thank you so much. We have recorded today's webinar, so it will be available within probably the next 24 hours for members to view. And we'll be sending out an evaluation survey as well, per usual, and we ask that you share your input with us. We depend on it for developing future webinars and face-to-face live events. And we encourage you to visit aecmeets.org regularly. We have a very full, action-packed year in 2017 with 18 webinars on the books and our 2 major meetings and 4 extra meetings throughout the year. Hopefully you've all received your wall calendar from AEC by now, and if not, please contact me. I'll be happy to send you one. We do have another question, gentlemen. If we use a worn dummy block, will it affect the flow in the die?
You're going to tend to increase your skin on the liner, and as the liner skin gets thicker, you're going to have more flow of that into your die. So yes, we want to manage the skin, and as the skin gets thicker, you're going to have more oxides and inverse segregation on the inside of your liner, which, unless you increase your butt thickness to retain it, will flow into your shape and give you surface defects.
Great. Thank you.
The best extruders today are running a cleanup block once a day and actually weighing the skull that comes out of the liner. And the skull weight will give you an indicator of how your dummy block is functioning, also if you're getting any bellying in your liner. And I would say, again, basically 100% of the super extruders today are using the cleanup block to manage and indicate the skull thickness on the liner.
Okay, another question just came in. You mentioned pickup in one of your slides. What was that in regards to?
I'm trying to figure out what slide it is. I'm not sure if we talked about surface finish, but I don't think we actually talked about pickup. You know, pickup can be various things. It can be because you have a relieved bearing. It can be because you have a rounded bearing, which have very little to do with the container. Where the container gets involved is the temperature, the resulting skin between the dummy block and the liner, or any deviation as far as ovality in the liner is going to let, you know, inverse segregation and oxides flow into your profile at random. As far as pickup, I think you're more die bearing dependent. I don't know if that answers the question, but
It was a super extruder slide.
we'll go back for a minute.
While we're doing that, I just want to mention that our next webinar is just 2 weeks from today, so as not to interfere with the holidays. And Richard Dixon of Hydro and Rick Liscombe of Exco Canada will be presenting Perfection in Die Design and How to Fill It Properly.
I guess it could have been when we had the limit diagram. Just 1 second. Actually, we don't have pickup on again. We have surface defects and tearing once you're the right side of the red line, and that's alloy dependent. But again, pickup mag 2 silica. Yeah, I'm trying to find it. Maybe that's a good question to ask us afterwards. I'm not quite sure where it's at, sorry.
Yes, please feel free to contact Paul or Ken directly. They would be happy to help you, or call me and I'll put you in contact with them.
But, you know, the last couple of weeks I've been running around the world with Hydro talking about surface finish, so we're very current on the subject.
Okay, well, I think that may be all the questions we're going to have today. Also, I want everyone to be aware that we'll be opening our registration for the AEC March annual meeting and leadership conference. That will be March 23rd through the 25th at the Hyatt Regency Coconut Point in Bonita Springs, Florida. So that should be a great event. We're going to have an alumni event again, so we'll be having former executives that were involved in AEC in the past will be invited to that meeting. So it should be loads of fun.
Well, thank you very much for the opportunity, and hopefully we helped.
Absolutely. It was a great presentation.
Regarding the first question, if you could send us the email directly, I can share with you the equation. That's pretty easy. If you look at the equation, then you know what I was talking about. The longer the container, then you have a more reflection on the board. Okay, thank you.
Super. Thank you both again. That was wonderful. Thanks, everyone, for being with us today. And hopefully we will see you back in 2 weeks. And that concludes our presentation for today. Thank you again. Goodbye.
Bye-bye.